Hello everyone. In this video, we will be discussing back pressure in distributed systems. So let's get started. In fluid dynamics, back pressure is defined as the resistance or force opposing the desired flow of fluid through pipes. So in fluid dynamics, back pressure is basically the resistance which basically opposes the desired flow of fluid. Let's take the formal example from Wikipedia itself, which mentions that back pressure is the term for the resistance of is the term for a resistance to the desired flow of fluid through pipes. For example, tight bands can create back pressure via friction loss or pressure drop. For example, this is a sharp band which can basically cause a back pressure to the direction of the flow. So the flow is in this direction, but due to this sharp band, there is a pressure built up in the fluid. So this concept has also been borrowed in software engineering, where in distributed systems, in particularly in event-driven architecture, back pressure is a technique to regulate the flow of data. So we can relate that fluid has been replaced with data, ensuring that components do not become overwhelmed. Cool. Let's complete the definition. So in software, we redefine it as resistance or force opposing the desired flow of data through software. Why is this needed? This is needed when input is coming at a faster pace than we can process. So there is a faster data producer and slower data consumer. Consumer or processor, you can write. Since we cannot control the pace at which input is coming, we either buffer them or we drop them. So let's say some person is trying to post on Instagram. They are generating some requests. Now these requests, the rate of generation of these requests we cannot control. We cannot tell the person that, hey, just halt for some time, our system is melting down. We are not able to handle these many requests per second. This request per second is actually written in abbreviation as RPS. So we cannot control in general the pace at which input is generated or input is coming. So what do we do with these three requests? We can either drop these if we cannot process. That is one option. The second option is we buffer them. That means we store them in some queue. It can be some memory. It can be, let's say, Kafka, where we store the unprocessed requests. And as our system for processing becomes available, we will keep picking one by one. So this is the second option for buffering. For example, if server A sends 100 requests per second to server B, but server B can only process 75 requests per second. So that means even though 100 requests are coming, B can only process 75 out of them at a given moment. So that means B is running at a 25 requests per second deficit. Now what will B do? B can either drop the request from A or can buffer some of the request as long as it can. So buffering will be bound by the available memory. It cannot be that B can start buffering the request indefinitely. It will have some memory at its disposal, which will be used to buffer the request. So only till the memory is available on B's side, then only we can buffer the request. And dropping might not be acceptable. In general, if you start dropping the request, then it will not only lead to data loss, but it can also cause some issues. So what should be done? A more generalized scenario is, let's say we have three microservices, A, B, and C. They are relying on D for some processing of data. Let's say A is sending requests as 100 requests per second. B's rate is 10 and C's rate is 20. But D can only process as 50 requests per second. So total input is coming as 100 plus 10 plus 20. That means 130 requests are coming per second. But the output processing rate of D is just 50 requests per second. So the deficit, the delta value is 50 minus 130. That means D is lagging every second by 80 requests. 80 requests should either be buffered per second or should be dropped. So basically D is overwhelmed by A because B is sending only 10 requests, C is sending only 20 requests, but A is sending well above the limit of 50, which is 100 requests per second. So D can tell A to slow down, but A cannot tell the users to slow down. This we already discussed where we took the example of a user posting an Instagram image. So A tries to buffer and may eventually run out of memory because we already discussed that buffering will be bound by the available memory only. So A can eventually run out of memory or even crash if it is unbounded buffer. That means let's say A has 100 GB of memory at its disposal. Then A decides that 20 GB I will reserve for buffering. So it will try to buffer till 20 GB. After that, the request will start dropping automatically. But let's say this is an unbounded buffer. A is not putting any bound on the buffer size. So all the 100 GB is available for buffering. If all the 100 GB is used for buffering, then there is no space left for doing any processing, and this will lead to a crash. So unbounded buffers can lead to a crash. Even though A has crashed, but you see that due to microservice architecture, B, C, and D can keep functioning. So we note that either A or D could buffer. In this above example, we saw that A is doing buffering, but this buffering is totally dependent on the design, and D can also buffer the data. Because A and D are doing the communication, either A or D can start buffering depending on the contract. But the essential idea is that someone has to buffer. It is who that is important, and it is totally dependent on the design. So if we can control the rate of generation of the request, then we try to control. But generally, that is not controllable. Dropping is also not acceptable in most of the scenarios. So the only option remaining is buffering, which is good in most of the scenarios. Back pressure can even happen on the UI. In the above example, we took the example of a backend. But let's say on UI, a huge list is coming. Let's say 1 million lists are coming for rendering. Even though in the viewport, the screen that is visible to the user at a given moment, it can only display 100 records. Then should we render all 1 million records at once? The answer is no. So we have to put a back pressure. So it can only also happen on UI where a lot of things, say a huge list is coming for rendering. Back pressure as a topic comes under reactive programming, also abbreviated as RX. RX stands for reactive extensions. And we have some implementations like Rx JavaScript and RxJava. RxJava basically provides one class known as Flowable, which basically is a way to implement back pressure in Java. So in this video, we discussed what back pressure is, how this idea is borrowed from fluid dynamics. We took some examples, some scenarios like dropping, buffering, crashing, unbounded buffers. And then we took a look at the solutions that are available in reactive extensions. So that's all in this video. If you have any doubt or any suggestions, please feel free to comment in the video. And please like and subscribe and share the video. Thank you so much.